Okay, so hello everybody. I am happy to introduce Yan Wu today. She is a master student at ETH Zurich and is currently writing her master thesis with the Computer Vision and Learning Group, which is led by Siyu Tan. And today she will present two of her papers. The first one is her AAA paper, Neural Architecture Search as Sparse Supernet, and then her recent paper, Trilevel Neural Architecture Search for Efficient Image Super Resolution. So thank you, Yan Wu, for being here, and the stage is yours.
Thanks for the introduction. And hi, everyone. I'm Yan Wu, and we're glad to be here to introduce our works on neural architecture search to you. And firstly, I'm going to introduce our AAA work of this year, the neural architecture search as a Sparse Supernet to you. Okay. If you have any questions during the talk, you also feel free to stop me there. Okay. Well, since in the years of deep learning, well, a properly designed neural architecture is, as we know, is very important for us to fully explore the power of the deep learning network tasks. But however, the neural networks are typically handcrafted, and also, as we know, this process is usually very time and energy consuming. And also these handcrafted networks are very likely to be suboptimal. So this year's neural architecture search is therefore suggested to automatically and also efficiently search for an optimal neural architecture design using the machine. And in the past years, well, in the areas of NAS, typical methods mainly include the reinforcement learning methods and also evolutionary methods. And recently also the differentiable gradient methods are shown to be very promising and also are more efficient than the previous methods. So in this work, we mainly focus on the discussion of this kind of differentiable gradient-based methods here. And I think you might know that in the class of differentiable NAS, a very popular framework is this one-shot architecture search. That is basically here we start from the supernet, which contains all the possible candidate architectures in our search space. And usually this supernet is optimized in a weight sharing way. And after we optimize this supernet, we select an optimal subgraph from it. And here to convert our discrete search space to be continuous, usually we employ the softmax or gunmax to combine the discrete operations in our search space. Yeah. So in this way, this supernet is built to contain all the operations and all the possible architecture structures. And usually most of the works, they still follow the dots. And after we optimize this supernet in a weight sharing way, well, what they do is to only retain a single most important operation between each node pair. And we name this kind of work as single path architecture search because they only have a single path between each node pair. But the problem here is that this kind of rigid constraint on the path structure is not good for the neural architecture search actually, because it can limit the search space of the architecture search and therefore it can limit the possible revolution potential of the neural architecture search. So this is not actually what we do not want to have here. And also recently, inspired by the success of feature aggregations in many successful multipath network designs, such as the inception network, and also, so some networks, they begin to search for such kind of multipath architecture, where they want to have the possibility to maintain multiple paths between each pair of nodes here. But to our knowledge here, that this kind of work, they typically also need to fix this aggregation intensity in advance of search. So this actually have the same problem as we have in the single path architecture search. That is, they usually have a fixed path structure here. And also, both in these two classes of work, single path and multipath architecture search, they usually have a fixed node number here. That is, within each cell, we have a fixed layers. And actually, this can also limit our search spaces as well. So being aware of these limitations in the search space of previous works, here we are motivated to remove such limitations in our search space, and we want to explore in a more general search space, and hopefully we will get a better architecture from such a more general search space. Yeah, so here we when we are implementing the neural architecture search, what we want is that we want to remove as much as human intervention as possible. So here we want to relax the constraints on the parse structure and relax the constraints on the node numbers here. And we name this as mixed path architecture search problem. And we expect that when we optimize this supernet, we want this supernet can automatically select which operations are useful and which nodes are useful, and we do not have any constraints on the numbers of paths between each pair of nodes or the numbers of nodes. Okay, so this is basically our motivations and goals here. And to approach our proposed mixed path architecture search problem, and we suggest such a sparse supernet modeling here. And we still follow the supernet modeling in previous works, and we also search for basic cell architectures. And the cell is also modeled as a directed acyclic graph following the dots. And to approach this mixed path architecture here, and we model this mixed path architecture as a specified version of our supernet. So we propose to approach this mixed path architecture by specifying our supernet when we optimize this supernet. So to achieve that, similarly, we first convert our discrete operation search space to be continuous, of course. And here, slightly different from previous works using like submax or compact submax combination. Here, we simply model the output of each node as a linear combination of all the output from our candidate operations. And each operation is weighted as a weight A here, and the A here can be any real number here. So for each cell, we have a weight matrix A here indicating the contribution of each operation on each edge. So each row here basically indicates the contribution of different operations between one pair of nodes. So the first row is for the first node, and the next two rows are for node 2, and so on. Yeah. So what we need to do now is to specify the weight matrix A here so that we can specify the supernet. These operations with 0 weights in our weight matrix A can be removed, and the nodes with all the incoming edges weights being 0 can be removed as well. Well, to specify the weight matrix A here, we employ the sparsity constraint, and we apply sparsity constraints on our weight matrix A, so that when we optimize our supernet, well, this supernet can learn to automatically select the useful feature maps from useful operations and useful nodes. Yeah. And because here we want to specify both the operation and also the nodes, we suggest a sparse relaxation of sparse supernet using this sparse group lasso. And the sparse group lasso term is a combination of lasso term and group lasso term. And here we group the weights of the incoming operations for each node as group. So here, the lasso term here on each weight element has to specify the operations, and the group lasso term here has to remove useless nodes in the supernet. So finally, this mixed sparse group lasso can achieve a good sparsity on both the operations and on the nodes. And then we come to the optimization. We formulate our problem here, and our optimization objective including, this is the normal one in the DOS, and here we have our sparsity constraints here. And we still follow the bi-level optimization framework. That is, we alternatively optimize the weight matrix A and the network parameters omega here. The difficulties here is that when we optimize the weight matrix A, because we have a sparsity constraint in our optimization objective, and this sparse group lasso term is not differentiable. So the classical gradient descent optimization methods, such as the SGD or ADAM, is not a proper method here because it cannot deal with the non-differentiable optimization problem quite well, and it cannot give us exact zero solutions. So here we finally turn to the proximal method, which is more proper here in this case to deal with the non-differentiable sparse optimization problem. And in this stochastic optimization setting, this accelerated proximal gradient optimization method, the APG, is a very efficient proximal operation framework. And the core in this proximal method is to compute this proximal operator, but it is not very trivial to directly compute the analytic solution of the proximal operator for this mixed sparse group lasso. We notice that in sparse group lasso, actually the lasso term and the group lasso term, they form a hierarchical structure. And to make it to be more concrete here, well, the sparse group lasso term has a L1 lasso term for each element, and the group lasso term contains each individual L1 term. And therefore, the group lasso term actually hierarchically contains our lasso term in the group in the sparse group lasso. So we can compute the proximal operator of the sparse group lasso in a hierarchical way. That is, we first compute the proximal operator for lasso term for each element in our weight matrix A. And then we compute the group lasso proximal operator for each group, that is each node in our supernet. Yeah. This is how we compute the proximal operator in our optimization framework. And we formulate our optimization framework here as a hierarchical APG. And the proximal operator for lasso term and group lasso term have their analytical solutions here. And in particular here, we suggest to progressively increase the lambda parameters here in our optimization objective. And as you can see, the lambda here actually controls the sparsity constraint strength. And intuitively, that is to say, when we, at the very beginning stage, when we optimize the supernet, and we want to optimize all the operations quite equally, and then as the optimization going on, we want to select useful. We want to select useful operations by increasing the lambda parameters here. And also, this progressively specifying strategy also proves to be very helpful to stabilize our supernet optimization process. Yeah, and this is basically. We also have another variant of our optimization framework, and we improve this very simple gradient descent step here in our original HAPG by a powerful Atom update here. And we formulate this improved version here, and we name this as Atom HAPG. And also in our experiments, you can see that Atom HAPG is helpful and more powerful. And yeah, this is basically how we model our problem and how we propose a new optimization framework for our sparse group lasso regularized optimization problem. And we test our proposed algorithms on both convolutional neural architecture search and recurrent neural network search. And yeah, I can firstly show you some architectures derived by our algorithm, and you can have a quick impression of what kind of architectures we finally can get here. And the first two cells are the results from the convolutional neural architecture search, and they are the normal cell and the reduction cell respectively. And the last one is the recurrent cells. And very interesting, you might see that is here in the reduction convolutional cell, you can see we only have two intermediate nodes remained. That is, we here remove two useless and redundant nodes in our supernet. Yeah, and you can see we have a very general path structure here. For example, for some nodes, we can have multiple incoming operations from the previous nodes. And for some nodes, we maybe only have a single operation to be connected to this node. Yeah. And here are some quantitative results of our experiments. And this is the convolutional neural network search results on CIFAR. And as you can see here, our sparse nodes with HAPG and Atom HAPG, they both outperform the original dust, both the first order and the second order. And also we transfer our results from CIFAR 10 to CIFAR 100. And you can see we also outperform the original dots. And then we also transfer our results searched CIFAR10 to ImageNet. And you can see our sparse NAS with AutoML HAPG achieved the best performance among our competitors. Yeah. And for the recurrent neural network search on PDB dataset, well, here we notice that the sparse NAS with HAPG optimization framework, it suffers from the gradient exploding problem here when we train this recurrent neural network. And here, this AutoML HAPG proves to be very helpful to stabilize the training of the recurrent neural network. And this derived architecture with AutoML HAPG here, you can see achieves a new state of the art. Yep. And basically, this is about this work. So in this work, what we do is that we enlarge the cell search space here. And this, as you can see from the experiments, it proves to be helpful and beneficial to explore the revolution potential of NAS better, and we discover some very interesting architectures, and this architecture really performs quite well. But the cell architecture design is not the complete story when we design a neural network. For example, sometimes we also need to consider the network level topology. That is how we stack those basic cells. And here, those cells are simply stacked in a fixed topology. And in some applications, maybe exploring the network level topology is very useful and essential. And also, for the operation in our search space, the channel number design is also very important, but it is not explored here as well. Especially when we want to derive an efficient network, the channel number design is very important for us to compress the network. So in our recent work, the Trilevel neural architecture search for efficient single image super resolution, and we developed a TrilevelNAS framework specifically for the image super resolution task. And we not only considered the cell architecture design, but we also include the network level and operation level into our search space. Yeah. And I introduce more technical details later. And firstly, a very brief introduction to our task here. And here the framework is designed for the image super resolution task. The task here is very simple. Basically, is that we want to recover a high resolution image from a low resolution image. And these years, there have been many deep learning-based methods proposed to address this super resolution problem. And in these areas, one of the research directions is to build an efficient image resolution network so that we can run our models on some resource-constrained devices. So many efforts have been made to design an efficient network with a small parameter size, less flop consumptions, and also low latencies. And of course, at the same time, we wanted to maintain its performance as much as possible with a small parameter size and less flop consumptions. And this is why this motivates us to build a NAS framework for it to search for an efficient and well-performed architecture for super resolution. Yeah. And the deep super resolution network, they usually are constructed with several convolution blocks and also a few of upsampling layers to enhance the resolution, of course. And we noticed that these network designs, they usually differ in the following 3 levels. And the top level, we name it as the network level design. Since for the super resolution problem, as we know, a key problem is how to perform the upsampling here. So here we want to find an optimal stacking way of these convolution blocks and upsampling layers. And this is what motivates us to explore this network level architecture design in the NAS framework, and we think it is very essential. And also the operation selection and architecture design of these convolutional blocks is, of course, very important to improve the network encoding capacity. And we name this as a cell level design. And this is what has been extensively investigated in the community of NAS. And further, the channel number design of each operation in the network is also crucial here, because here we want to get an efficient network. So we name this as kernel-level design, and this can be a very important trade-off of the model efficiency and the model capacity. So far, this forms as a tri-level neural architecture design space, and it's almost impossible to manually explore in such a huge tri-level design space. So this motivates us to build an automated NAS framework for it to explore in these 3 levels simultaneously, so that we can derive lightweight and computationally efficient deep resolution network from it. And at the same time, we want this network is also well performed with a smaller model size and less flops consumptions. Yeah. And actually, there have been several existing NAS framework for this resolution task. And one of them is this hierarchical NAS. And in this work, they propose a reinforcement learning framework to explore in network level and the cell level. But in this work, the kernel level is not explored here. So their derived architecture is very heavy and is not efficient enough. And also this kind of reinforcement learning framework is not very efficient and cannot be scalable to very large search space. And another work, the autoGAN distiller, the AGD, they propose a differentiable NAS framework to explore in cell level and the kernel level. But the network level is something that they did not explore in their work. So basically, starting from this work, we want to further include this network level search into our search space. So I mainly focus on the discussion of how we design our network level search framework here. Okay. And firstly, I want to illustrate our network level search space design. Well, here we mainly focus on the AGD backbone design and also as a fair comparison to HGD. And here the main body part of our network is constructed with 5 residual in residual blocks and 2 convolutions here. And in our network level search, we want the network to have a searchable path of these residual in residual blocks and these upsampling layers. And also here we want that our network to have a searchable depth as well. That is, here in our original SuperNet, we have 5 residual in residual blocks in total. But it is possible that maybe these 5 residual in residual block, not all of them is necessary to have a well-performed network. So in summary, our search space include all the paths with at most 5 residual in residual blocks and 2 upsampling blocks. And we actually additionally propose a new backbone here instead of using the original HGD backbone. And our new backbone proves to be more efficient and computationally light. Yeah. Here we replace these 2 upsampling layers with a single pixel shuffle layer, and we fix this pixel shuffle layer at the top of the network. And the search space here kept to be the same. That is, we also want to have a searchable path of these convolution layers and these residual blocks. And also we want to have a searchable depth here. And this is how we design our network level search space. And following the general idea of the differentiable NAS, we want to build a supernet. That this supernet is supposed to contain all the architectures in our network level search space. And to do that, well, actually one of the previous work, the AutoML, they have proposed a Trilevel Supernet modeling to design a network level supernet. And this is how they build this Trilevel Supernet. And starting from the input node, the information can flow either along the horizontal arrows or along the vertical arrows. The horizontal arrows and the vertical arrows here indicates the residual in residual blocks and upsampling layers here in our case. And the information will keep flowing in this way, and at each intermediate nodes, the information can flow either in vertical way or in the horizontal way, and until they reach the output node. So in this way, they build a very compact supernet. And this supernet contains all the possible paths which can travel from the input node to the output node. But although this kind of modeling is very compact, but as we can see here, within this Trilevel Supernet, the different paths information flowing is highly entangled. So it is not very easy for us to tell which paths contributes more to this supernet. So it is not easy for us to disentangle them and to select a final optimal subgraph from this Trilevel Supernet. And also this kind of Trilevel design, it naturally does not allow us to search for the network depths, because the network depth here is always fixed, because we only can travel from input node to the output node here. So here we propose a new tree supernet design here. And as you can see in this tree structure, the information can flow either along residual block or along the upsampling layers. But the information flow in this tree structure is more disentangled than the Trilevel Supernet. And also this kind of modeling way allow us to search for the network depths. And I'll show you later how we do that. Yeah. Well, based on our tree supernet modeling, and firstly, we want to relax our search to be continuous here, of course. Now we model the output of our supernet as a weighted combination of all those intermediate feature maps. And the weights here indicates the feature map contribution to the supernet. And as for this combination function for each intermediate feature map, and a widely used function is the submap combination. But as we know, the output of submax is comparatively uniform and is not sparse. So usually an additional hot discretization step is necessary to sparsify the output by only retaining the element with largest contribution. And this is known as model discretization. But however, this discretization step will introduce a large model discrepancy between the supernet and the final derived architecture. And so here, to bridge this model discrepancy, we suggest to use a new sparsely-mixed function here. And the output of the sparsely-mixed function can converge gradually to a single architecture. So with this sparsely-mixed combination, we can diminish the model discrepancy here. And also based on this tree-like supernet modeling, we can obtain a network with flexible depths. For example, if the output of the sparsest maps finally converge to, for example, this feature map here, we can accordingly take this path as our final path. And therefore, these useless blocks can be pruned, and we can get a more efficient network and a more shallow network from it. And here we want to further encourage our supernet to prune more useless blocks, because we want to get more efficient networks from it. So we additionally introduce a weight ordering constraint here. And this constraint basically will encourage the parent nodes in our tree structure to have a large contribution than their children nodes. So this essentially encourages a descending weight distribution along the tree depths. So in this way, our supernet can be optimized to strive for a trade-off of the network capacity and the network depth here. Well, finally, we formulate our sorted sparsely-mixed combination here. And this can encourage our supernet to converge to a single and a shallow network. And this is basically how we build our network level search. And as for the cell level search, we did not play too much here. And we only include 4 operations in our cell level search space, and we build a SuperCell for it. And we also employ the sparsely-mixed combination to combine those candidate operations in our search space, so that we can also diminish the model discrepancy in the cell level search as well. Yeah. And then in the kernel level, for each operation in our operation search space, following the AGD, we build a SuperCell for each operation, and this SuperKernel for each operation. And the SuperKernel has the maximum channel number. And for each operation, we define a set of expansion ratios. And we use sum-by-sum-max to sample from this set of searchable expansion ratios. And then we update the corresponding subkernel. And in this way, we optimize the sampling probability of each sampling ratio for each operation. Yeah. So far we have relaxed our trilevel search space to be continuous by building a Trilevel Supernet. Yeah. And then we go to the optimization stage. Yeah. And as we know, a general framework in the differentiable NAS framework, they usually have such 3 steps. And at the search stage, we train the supernet in a weight sharing way. And then we need a model discretization step to get an optimal subgraph from this supernet. And then we train this final architecture from scratch. Because here we employ the sparse-mixed combination here, and in the search stage, our supernet can already converge to a final single architecture. Yeah. And so we can diminish this model discretization step here, and we can directly inherit the architecture from our search stage. And this also can enable us to directly inherit the network weights of the supernet from the search stage, because we do not have any discrepancy between search and training stage. And this can help us to save some training costs as well. Yeah. I can show you some of our results here. And here we benchmark some manually designed super resolution model here. And we also benchmark some NAS framework for super resolution, including the TPSR, which is a 1-level NAS, and also the AGD, which is a bi-level NAS framework. And we also benchmark the Trilevel Supernet as a comparison to our Tree Supernet by combining the AGD with the Auto Deep Lab. Yeah. And the last 2 rows are our results. The TrilevelNAS A is based on the original AGD backbone design. If you still remember that, I have the 2 backbone here for you. And the TrilevelNAS B is based on our new proposed backbone here. And from the results, you can see our TrilevelNAS B, it has a much smaller parameter size and the flops consumption than the TrilevelNAS A, especially the flops consumption. But it still have a comparable PSNR performance. Yeah. And also both the TrilevelNAS A and the B have a comparable performance to our competitors, but the parameter size and flop consumptions much smaller. Yeah. Yeah, this TPSR, they have a very tiny network, but they really have a large search cost, as you can see here. And in this radar plot, we give a complete comparison between our methods and all these other methods in 3 aspects. And the one aspect is the search efficiency, which is indicated by the number of GPUs they used and the search cost. And also we compare the model size and the flux consumption, and also the PSNR values, which is the performance of the super resolution network. And you can see our method is the red areas. You can see our method is a good trade-off. It achieves a good trade-off between all those metrics here. And here are some visualization results. And the last 2 rows are from our results. And these are from other methods and also the ground truth high resolution image, as you can see. And our TrilevelNAS A and TrilevelNAS B, they have comparable visual quality to other methods, but from the bottom you can see we have a smaller model parameter size and the flops consumption. Yeah. Yep, that's basically what I want to share today. If you have any question or comments, and they are both welcomed. Yeah.